Welcome to an OpenAeros update video. Today, all about the OpenRespirator. Now, this is a project we kicked off about a year and a half ago to think about what are the great features and design considerations that have to go into a good mask, and maybe someone might argue the world's best mask. So, what are those things? Well, of course, there's always filtration efficiency. That's critical to any good design. But there are other considerations like comfort, how easy it is to breathe in, how does it seal against your face, is it comfortable? But other things like how easy is it to take on or put off? Portability, can I fold this mask in half and stick it in my pocket? Economic considerations, things like how much did it cost and what's the total cost of ownership? And of course, considerations around looks and fashion. Sometimes you want a mask that stands out and says, hey, I'm wearing a mask. And sometimes you want a mask that just blends into the rest of your outfit. Now, of course, there's always some very important part of mask, and that's the most important part. And you hear me say it a lot, fit, fit, fit. We need a mask that also fits a huge range of faces. So this is a huge task. But the good news is that there are some masks out there that kind of give some clues about where we can go. This example is from Prentex Breathe. Now this mask is cool. First, it's all black, so it gets points in my book, but also features an elastomeric seal. The elastomeric seal does two things. It helps with the fit, but also it helps with the facial comfort because you don't need as much sealing pressure. Now they had considerations for both ear loop and headband attachment, which makes it a little bit easier to don and doff or take on and take off. Now, one of the limitations of this design is that it used a flat filter design, which means that you only had limited filter area. So if you wanted high filtration efficiency, you had to make the trade-off with breathability. And if you wanted really breathable, well, then you wouldn't necessarily get the filtration efficiency. Now, there are some improvements to that you could have, and they made the Breathe 2. This one has a test port put in from an experiment a while back, in which you can extend the area of the filter, which helps with the breathability. But as you make the filter bigger, so does the mask. The question is, could we overcome all of these in a single design? Now, the answer is kind of, and I'll show it to you. This is the OpenRespirator right now. Now, what you might think is, Aaron, that's really not that cool. And I agree with you. But what is here is some of the important design features that got us there, and the tools and techniques that we use to prototype it actually are probably the most interesting thing about it. Now, there will be a call to action at the end of the video because I think that we can make a much cooler mask, and we could use your help. Now, this project has taken about a year, and so I wanted to bring in one of our engineers who's been helping along the way. So, John, welcome.
Thanks for having me, Aaron.
All right, John, so this is a really okay design. We're good engineers, but not great artists. But let's talk a little bit about the techniques that we use to make this mask. Now, when we started, we had some different ideas about how we would start with. We used some classic clamshell style molds that were 3D printable because for those not familiar with LSR, it's traditionally very expensive to make. If we were to make this out of machine metal and go the traditional route, these molds might be $50,000 to $100,000 for each run, which would include that prototype. And the economics of masks, maybe a few dollars each, it takes a long time to get that money back. So we kind of did a different route, which was to 3D print those multi-component molds like this one here. Can you walk me through a little bit about how they work and what were some of the trade-offs in terms of timing that came with them?
Sure. So this is an example of a traditional style mold that's a clamshell. This one is 3D printed, and it has 3 pieces. And this is a mold for a respirator body. And the more features you add to a mold like this, the more complex it gets. This one has 3 pieces. It has parts for clamping and ejection ports. And the more features you add, the more time it takes to make that mold. You can see you can get much more complex. This one had some overhangs, and so we have cores that move in and out of the mold. And if you want to add co-molding to a mask or a respirator, and a mold, it's even more complex. You're adding things to hold other parts inside the mold itself.
And walk me through, so how long does it take roughly if you had a design like this? How long would it take you to design a mold and then be able to shoot our first test article?
Sure, it might take, once you have a digital design for a respirator, it might take up to a week to create a mold from scratch. And then if you had any changes, it might take 1, 2, 3 days to update the mold to accommodate those changes, depending on how complex the changes were.
Yeah, so one of the challenges that we had, although this method is much cheaper than the classic machining methods, it still had a lot of limitations in terms of how long it would take. And if we added a feature around the nose or something like that, we would have to add extra mold features, which would just take a lot of design time.
Yep.
So one of the things that we added to this created for this project. So we call this the digital-to-silicone model concept, and we have it all kind of represented in this little simple mold here. Now, one of the things I didn't talk about yet in this design is that our filters are removable. Now, this design had a couple challenges that John hit on, this concept of co-molding. In this design, we have a PETG frame that's embedded within the silicone. It also includes the attachments for the head strap. So not only do we have a silicone feature, we also have a plastic feature. Now, what is really cool in this mold is that we actually introduced a third material, polycaprolactone, or PCL. It's a heat moldable material, something that you might find traditionally in like a mouth guard or something like that, which would allow us to heat the mask up and form the mask to fit your face. Now, traditionally, if we use those classic molds, it gets pretty hard, John, right? Because we need to fixture the plastic pieces, we need to fixture the separate polycaprolactone, we got to shoot it and then take it all apart.
Yep.
Now, walk me through why the digital silicone process is a lot faster and how you went from a CAD model kind of design like this to a mold to a finished good.
Sure. So, just like in any traditional molding application, we first start with the piece or component you want to mold. And so in this case, it's a respirator body. We created this using SolidWorks on a PC. We include all the different components, like Aaron mentioned, of the mask. And then once we have a digital file, we can create a mold around it. And essentially, this is just a block of material with the negative of the mask removed. So we basically have a cavity where the silicone will be inside of here. And this mold was created using a 3D printing process that was multi-material. So we're able to print 3 materials all at once, all in one piece.
Okay, now John, you're saying one piece. So the other molds we take apart to get the material out after we shoot it with silicone. In this mold, we print this mold out, and we used just a commercial printer, right?
Yep, it was a Prusa XL5 tool.
Yeah, so that's just an off-the-shelf printer that can do multiple materials. We print it out, we pull it off the printer, we inject it with silicone, let it cure.
Yep.
Okay, but it's one piece. So how do we get the part out of the single-piece mold?
That's the magic here. So the mold body itself is printed out of a material called BVOH, and BVOH is water-soluble. So once we've injected this with silicone and let it cure, we can put it in a hot water bath, wait about an hour, the mold body itself will dissolve, and you'll have your finished part.
So one of the big advantages of this technique is that we don't have to have any design considerations for like overhangs and like the other stuff that we had to do with the prior version. We get all of our co-molded parts in at the same time.
Yep.
But here's the real question. How long does it take you to go from this part to the finished to a mold and then to a finished part?
Sure. So if you have a design change on here, that design change to go from one mold to the next mold, which is kind of our iteration process, it might take an hour to make the design change on here. To change the mold, it might take another hour. And then once you've made that change, you put this slice it and send it to the printer. It takes about 24 hours. So 24 hours and you've gone from design change to a mold ready to shoot.
And then maybe 30 minutes for it to cure, another 30 minutes. So within roughly a day's time or a couple of days' time, you have design change whatever you want without really any geometry considerations to a fully functional design. Okay, but the question is, how much did our capital set cost? So how much did it cost us to build all the capital?
Sure, the printer was about $3,500, $3,500. Materials cost for this, for a single mold is about $30.
Yeah, so that's incredible. So we took basically what would be classic machining, 50,000 to 100,000. We reduced that with 3D printed versions, which has been very common. People have been doing that for a while, but that had a huge time. So now we not only have a very cheap process, but now it's really fast and very quick to iterate, which is what we've really been after, and that we discovered that we have to be much faster at iterating because we're not great at designing respirators yet. So we made the mask body, but the next problem is we need filters.
Yes.
Okay, can you walk me through a little bit of how we designed and prototyped fully functional filters?
Yeah, sure. So if you can see, these filters are pleated, and that means we can get a lot more filter area in a smaller space. If you can see here, this is a template to cut out filter material. You can see there's a lot more surface area there than the size of the filter here. We'll talk about how we made the silicone mold and the pleating. So you can get traditional or industrial machines to do pleating for you, but we wanted to create a solution that was easy to use. You could print out on a 3D printer, and it was very approachable, and anybody could do it. So the first step was to pleat the material, put that pleated material in a mold, and then inject it with silicone. So for this process, we used a more traditional mold. Obviously, we can't get the filter material wet, so we couldn't use a D2S process with the water-soluble mold itself. So we went with a traditional style mold, and that mold is the clamshell type here. One of the interesting things we did do, though, is we had this filter core here. And to pleat the material, we take the filter core and add it to a fixture. We can then cut out our filter material using this template, and then insert it into the filter core, and one by one create the pleats of the filter. So we do one pleat, and then we'll add a second pleat, so on and so forth, until you've created all the pleats for your filter. And then one by one, you can take these out, insert a metal pin that is held in place by a magnet, which will hold the media into the pleating core, and then the two cores stick together with magnets. And now you have a pleated filter held in place, ready to be inserted into your mold. You can insert it in your mold, clamp your mold, inject it with silicone. 30 minutes later, you have a pleated filter that's fully functional.
So now, one of the things, like unlike the respirator, we don't really change a lot of the geometry. So in this design, we can just easily update pitch of the pleats, we can update the thickness, and generally we're going to kind of be in a general shape like this. So
yep, so it doesn't really add a lot of time for mold design changes. Yep.
Okay,
there are no complex features like that, like in the respirator.
Right, in the respirator.
Yep.
Now, I know most of you are asking, like, okay, you did all this, but does this thing really work? And the answer is, we actually tested this in Aaron's lab, aka my bathroom, and doing an ambient aerosol measurement like we have typically done. This design, we were able to achieve over 99.9% filtration efficiency, and we actually have pretty dang good breathability. So what we managed to do, as I reassemble it here on camera, it always takes longer than you think when you're trying to do it live. So what we managed to do is create a fully functional prototype of a silicone mask made from the silicone material that you want. Sometimes other 3D printing processes use different durometers or different type of materials, but we actually were able to prototype it directly when we want, in the durometer that we want, and make fully functional pleated filters. So we were able to make a fully functional respirator, all from some simple prototyping equipment. Now, I think the first thing that me and John will acknowledge, that while we might be pretty good engineers, we are not the most artistic. And one of the things that we're looking to do is get some help in the space. What we're interested in is, as we develop these innovative tools that be able to allow people to prototype, we want to work with artists or industrial engineers or people who have maybe had a great idea about a respirator, had an idea to use some elastomeric material, but had looked at the $50,000 or $100,000 bill that they might face to make their first prototype, and we'd like to partner with you. So it is going to be open source. In fact, all of the tools we're talking about today are available in our GitLab account below, along with a companion video and a whole bunch of other information about how to do it, but we'd like to do it open source. So this means that we need some help, and we'll have to figure out how to make that work for you. But if you can, reach out to us. You can reach us at an email, icanhelp, ICANHELP, at OpenAeros. Send us an email. We'd love to find a partnership or way in which we can help and explore what is possible with these new techniques that we had. So with all that said, John, I think this has been a really exciting project. We got a lot more ahead of us, so stay tuned for some more videos. But thanks for watching, and hey, at least we made a real functional mask this first time, so that's pretty exciting. So thanks for watching, and we'll catch you on the next one.